Hello. It is the 18th of December, 2015, and this is the Unseen Podcast, episode 37. I'm your host, Paul Carr, and with me tonight are Adam Smith.
Hey there, Paul.
Hello,
Pleasure
Adam.
to be here again.
And James Garrison.
Hello, everybody.
And Patrick Festa.
Howdy, howdy.
Okay, well, this is the last Unseen Podcast of 2015. So let's talk about some of the things that have happened recently and maybe in the last calendar year. Now, I have to tell you, I have somewhat of a bias against arbitrary time divisions, although it doesn't. I know that the culture I live in cherishes them very much. So we'll talk a bit about some things that have happened in 2015, and that will hopefully clear the plate for 2016 when we return on January 8th. So one of the things that's happened recently is some really sharp new images of Pluto have come down. Have you guys seen that?
Oh, yes.
They're some of the highest resolution images. They're highly processed, but doesn't mean they're not valid. It just means that they had to do a lot of work to get what you see on your screen. We'll have a link in the show notes to some of these images. Or just go to pluto.jhuapl.edu and it's easy to navigate your way to them. Adam, what did you think of them?
I think they're stunning.
Yeah.
Absolutely stunning. It's the amount of diversity in Pluto in particular is totally unprecedented. It's not at all what I was expecting.
Yeah,
I don't think anyone was expecting.
Yeah,
Pluto
me either.
I
was thinking you'll see some craters, and you'll see maybe a few features, but nothing like this. This is very detailed landscape. And
if anything, I expected it to look a lot like Triton.
Yeah.
Do you remember the pictures of Triton?
Was this very recently, or were these like weeks ago?
Oh, I think it was about 10 days ago, wasn't it? Yeah.
Well, then I definitely missed them.
Oh, well.
Yeah,
you should.
There are some brand new images.
Yeah. If you are watching live, I'll try to put up a link. The new images are extremely sharp, high resolution, as good as we're ever going to see a Pluto for probably at least one human lifetime, if not more. And they are in color. They've put in the color corrections and everything, and they are absolutely stunning. As I agree with Adam on that. Just go to pluto.jhuapl.edu. You'll see one of the marquee images right there. And it is, you see this very, very sharp division between what looks like some kind of ice flood. I'm not sure that's the right term, and these mountains, which I think are also made of ice.
I think glaciation is the correct term.
Well, from what I heard, that the mountains are literally made of water ice, which is not usually that strong, except Pluto is so cold that the ice is literally like rock.
Yeah.
And the methane and the other gases wouldn't be strong enough ice to support that tall of structures.
Yeah, well, I certainly think that Alan Stern and his science team have been completely vindicated in saying that this is going to be an interesting world to visit. it's actually Pluto. Alan will tell you that Pluto is a planet. I'm not going to get into that discussion right now. What's a planet and what's not? But the interesting thing is that it's a lot more varied and active and interesting than you might have thought. You think these Kuiper Belt objects, which Pluto is also kind of a Kuiper Belt object, should be kind of dull. There should just be a few craters, maybe some rills or other simple geological feature. Nothing this complex. So this is something the planetary scientists are going to be chewing on for years to come. And I think it may ultimately feed back into our understanding of everything else in the outer solar system. So, and I think that this and Cassini have together really revolutionized our view of that.
There's some interesting science results starting to emerge from Pluto. I mean, they haven't got even half of the data back yet, but already there are some very interesting papers being written about Pluto.
Right.
That there was a meeting just recently, the American Geophysical Union meeting in San Francisco.
It's this week, I believe.
Where I think it's just ended, probably today.
Mm-hmm.
Someone's done some initial crater counting on the surface of Pluto, and there seems to be an absence of small craters, which suggests that there may be far fewer small Kuiper Belt objects. It was thought that there would be a lot more very small Kuiper Belt objects, and the lack of small craters, in particular on both Pluto and Charon, suggests that they may well be, Kuiper Belt objects may well, in general, be a lot bigger than we suspected, which is interesting. New Horizons will get a good look at a Kuiper Belt object, a small-ish Kuiper Belt object, in, I think, New Year's Day, 2019 is due to fly by its next target.
Just about 3 years from now. Yeah.
Yeah. Also, shows you how big the Kuiper Belt is.
Oh yeah.
Also, I mean, I didn't see the most recent, the last 10 days, like you were saying, but one of the most fascinating things was that this crater count and stuff that they're doing, the fact that Pluto is geologically active with ice, and the surface itself is apparently newer than they expected. It's to the scientists, the planetary scientists, it's very, very exciting to see that, like Paul said, it kind of blew away what they were thinking. They thought it was just going to be some quiet, icy ball out there, not much to see, but it turns out to be the most interesting thing they've seen in a long time. I mean, there's literally methane flows and other frozen gas flows as if they were like rivers and stuff, or not exactly like that, but various geological things going on, depending on what part of its orbit it's in. And in addition, like I just said, the surface itself seems to be younger than they expected it to be. That's the last that I've heard. I think that's already a month or more old.
Well, it's still showing signs of a recent tectonic and geographic activity, which is kind of strange for an object, especially a rocky or semi-rocky object that's that far out from, its parent star.
Yeah, well, and they still haven't answered all the questions how that's even where the energy comes from. So it's going to take some work. I think they'll get there, but this happens every time we go visit the outer solar system. We completely revolutionize. We realized that we weren't imaginative enough, and I think it makes a strong case for going to visit Neptune and Uranus, and not just a flyby, perhaps, but an actual orbiter. And
yeah, definitely.
Oh yeah, the various moons around all the gas giants are beckoning to be studied.
Now the problem though that is that you need to get that way up there in the outer solar system. You need to get any significant mass out there. You're going to need a bigger rocket, and so that's something that's in work. But the Atlas V that sent Pluto, this had New Horizons. Pluto is nowhere near big enough to do an orbiter. So unless we can find a way to build a really, really small spacecraft. So all that work is ongoing. And I know that even more than 10 years ago, Alan Stern proposed a Uranus flyby mission.
Well, they Juno's on its way, so they managed to do it with Juno, and that damn thing is a tank.
Well, Juno's not going anywhere near as far,
Right. Well, still, I mean, the way they did that one is instead of trying to get out there as fast as they can, they took a couple of years to go around the Earth a couple of times to get a little speed.
Well, so did Galileo. Galileo got an Earth flyby boost, but that Jupiter is relatively easy target. If you look at a 2-scale version of the solar system, Uranus and Neptune are way. Holy! Somebody mute, please. Everybody mute. All right. Okay. Thank you. Okay,
I believe that was James. I was watching the bar on his avatar go up.
Okay. Sorry, folks. I don't know what that was. I didn't know that it was even possible. But now you've got it sampled for historical purpose.
Got me right in the chest. Oh man, that laser beam of his.
I almost ripped my headphones off.
I'm glad I wasn't wearing mine.
Yeah. James, try unmuting just for a second. See what happens. There was a horrible feedback.
Yeah, nothing's happening.
Okay, you're very, very distorted, but other than that, okay. Sorry, folks, for all this audio engineering going on live. Okay. Yeah, we had some kind of feedback event there. I don't know what caused it.
You just started on my end. All I heard was you skipping.
Okay, we had massive feedback. I don't know what caused it. I can probably notch some of it out. But anyway, let's continue.
I just want to make a quick suggestion. James, I had just made a video last night about specific audio problems on Google, and you sound like a perfect candidate for what I was talking about. Are you running other software for audio and stuff like that?
Let's not get into that right now. Okay. Let's continue talking about planets.
There's been some interesting work done on Pluto's smaller moons, Nix, Hydra, Kerberos, and what's the other one? Oh, it's eluding me at the moment. But they're very strange.
What's strange about them?
Well, most of the moons in the solar system, including our moon, are tidally locked, and they have a synchronous rotation, so they always keep the same face towards the planet.
Mm-hmm.
Pluto's smaller moons don't do that at all. They spin much faster than anticipated. Hydra, it spins something like 89 times in one orbit, which is ridiculously fast. And, they haven't quite worked out why that is, but they have very chaotic orbits, and it it may just be down to the gravitational torque induced by Charon, but that's an interesting work in progress to understand the motion of the small moons, because they don't orbit at all how scientists predicted they would, and they look like they may be mergers. If you look at the pictures of the small moons, there's definite evidence that they're each not one body. They may be mergers of smaller objects. So that's interesting. It's possible that they may have been the product of the giant impact that produced Charon initially. It would obviously have created a lot of debris, and some of that debris has come together and merged to form these small moons. Why they orbit so chaotically will be worked out, I'm sure, by someone very clever at some point.
Yeah.
The other really interesting thing is, have you seen the pictures of the cryovolcanoes? What might be cryovolcanoes?
I only saw some reference to that today, but I didn't get a chance to look at it.
There are two big mountains on Pluto that are each several miles wide and a couple of miles high, and they have a hole at the summit. On Earth, that suggests a volcano.
Right.
So on Pluto, it suggests cryovolcanism, which would be some sort of slurry of probably water ice that contains ammonia, methane, something to act like an antifreeze. The cryovolcanism is very difficult. It's never been observed anywhere else in the solar system, because it's supposed to be very difficult to have the exact right conditions for cryovolcanism. The main thing it would need is some sort of internal heat source inside of Pluto itself.
Yeah.
So, you know,
and where's that coming from?
Exactly. How has Pluto managed to keep itself warm for 4.5 billion years, that far out in the solar system? That's incredible. It seems to suggest, if these are cryovolcanoes, that there is some sort of internal heat source, and that may well be driving a lot of the geological processes that we see on Pluto, the ever-changing resurfacing that's going on. I find it fascinating. It really is a fascinating dwarf planet, and it reaffirms my belief in why we explore, why we send spacecraft to look at these places. It just feeds my curiosity about what's out there, mm-hmm. and why things are the way they are, how things are the way they are.
Right, and there's, of course, we know there's an awful lot more Kuiper Belt objects out there that probably won't be explored for a very long time, if ever. But there's too many of them. So we're probably in our lifetimes, probably in our children's lifetimes, there'll only be the two. We just seen one, and the other one will be in 3 years. So we're in a golden age of Kuiper Belt observation. Now, Adam, we mentioned something about way farther and close to the sun. There was a successful orbit acquisition around the orbit of Venus by a Japanese satellite. Now, I should point out this was not as planned. They initially had intended to use a large thruster to get into orbit around Venus. That didn't work out for them. They came around again, maneuvered into position, and now used their secondary, what they call the attitude control thruster, to kill the energy that they had to get into orbit around Venus, and they've successfully gotten into orbit around Venus. It was quite a nail biter for all involved, and it was. And I followed it on Twitter following Emily Lakdawala, and she was retweeting some Japanese folks who understood the language well enough to know what was going on, and it was pretty tight there, but they actually did succeed. So now we have another satellite in orbit. The European Venus orbiter recently re-entered the atmosphere. Well, it entered the atmosphere of Venus. It never entered it before, so it was not a re-entry. So it's now the only orbiter around Venus, and it's an atmospheric mission to study the atmosphere of Venus. So, and the atmosphere of Venus is probably where the action is, right? As far as Venus is concerned. Could be all kinds of interest.
Yeah.
Anybody else follow that like I did?
I was listening to you. That's very interesting. I didn't know that the Japanese actually put an orbiter up there.
Yeah. Well, they had, I guess it was about 3 years ago. Failed.
5 years ago.
Yeah, 5 years ago they had failed to get into orbit around Venus.
Yeah. It launched, 2010, and it was supposed to go into orbit on December the 6th, 2010. It ended up successfully entering into orbit December the 6th, the very same day, 5 years later, 2015.
Wow, 5 years?
Yeah. So they sent it they sent it into hibernation, didn't they?
Yeah.
It flew by Venus. It was supposed to go into orbit. It didn't. So it flew by Venus and went into a solar orbit and traveled around the solar system for 5 years in hibernation before the Japanese engineers managed to get it out of hibernation, worked out the correct engine burns to get it back on track, and successfully entered into an orbit around Venus earlier on this month.
That
I don't think
itself is interesting.
Yeah,
it is. It's an incredible feat.
Does anybody know what science instruments are on it, or what is it? What is it supposed to be studying on Venus? You know, what types of?
Well, it's already sent back. It's already sent back images.
Oh yeah, we have a list right here. There's the lightning and air glow camera, which looks for lightning. Ultraviolet imager, looking for sulfur dioxide and so on. A long wave infrared camera, which studies the structure of the clouds. A 1 micrometer camera, which will image heat radiation from the surface rocks. And a 2 micrometer camera would detect heat radiation emitted from the lower atmosphere. And then they're also going to do radio science. By studying the signal coming back from the satellite, they'll be able to learn a lot about, just as they did for Magellan, they'll learn about the gravity and mass distribution of the planet. They're basically studying the atmosphere. They're also looking at the surface rocks, and they're looking for active volcanoes as well, because it looks like Venus turns itself inside out every once in a while.
So Venus is definitely active as volcanically or geologically, then.
Well,
right?
they think it probably is, but that's an open scientific question whether it's currently active.
I mean, it just seems to me, where's all that pressure come from? Where's all that carbon dioxide, the poisonous dense atmosphere come from if it's not?
Well, it got outgassed at some point, but the question is, how did it get so hot? Well, that seems to be classic greenhouse effect. They once it gets that hot, all kinds of naughty unpleasant chemistry can go on, and you get basically a surface that very hard to survive on, even if you're a machine. So
I always had the question, I always compared Mars to Venus, and I always had the question, in other words, we think we know how Mars lost its atmosphere to at least a point, we're thinking the magnetic field disappeared. So I'm thinking, am I right in saying that Venus must still have a magnetic field able to...
No, it doesn't have a very strong magnetic field.
So I'm curious.
But it's quite a bit bigger than Mars, so it hangs onto its atmosphere more easily.
I see. Yeah, that's something like 80-something% of the Earth.
Yeah, the weirdest thing about Venus, to my mind, is its rotation period. It's not unlike Mars and Earth, which have about the same rotation period, about 24, 25 hours. Venus is spinning the wrong way and very, very slowly. And nobody knows why that is for sure. That's, probably not a mystery we're going to solve easily or quickly. So the thing to do is just characterize the planet as well as we can, and then there's that whole everything is ripe for further study. That's why some people would love to land rovers on the surface. And everybody studies of... Pardon?
They would melt.
You can build hardware that won't melt at those temperatures. The question is, if the problem is it has to be very simple hardware, so all the smarts have to be somewhere else. And one of the best concepts I've seen is to fly a Venus airplane up higher in the atmosphere. The airplane would have all the intelligent electronics on board, and everything on board the rover would be very simple. And you wouldn't be able to get a lot of pretty pictures, but you could get science data. And that would be, exactly what you could do with it is something that would have to require some more study, but I think there's at least a concept for how you can make it happen. There are electronic parts that can survive those temperatures. There've been a couple
of mission proposals, NASA Discovery class mission proposals just this year, haven't there? To Venus. One was an orbiter, and the other one was a lander. Or something that would descend.
Well, drop-ons, that drop-ons are, and those two might be complementary, possibly combined into one mission.
It would make sense, wouldn't it, to combine them?
Yeah, I'm sorry.
But the funding cap for Discovery missions is pretty tight, so it might be tough to do that.
I'm so curious as to how the hell it's so, the atmosphere is so dense. I'm thinking in my limited scientific brain that it's got to be active somehow. It's replenishing its atmosphere somehow, because if it doesn't have a strong magnetic field, and it's so close to the sun that I would think that like Mars, it would blow its atmosphere away, and yet instead of getting thinner, it's 100 times denser than Earth's, and it's just a little strange to me. Something is going on there that's.
Well, the mass is much closer to that of Earth, whereas Mars is much smaller. So essentially, it's gravity that holds the atmosphere on. Now Mars lost its atmosphere. I'm sorry, Adam. I think I lost
the European Venus Express found that Venus has a tear-shaped atmosphere. That its atmosphere does extend, sort of trail behind the planet as it orbits the sun. The solar wind kind of blows it away from the planet. So I'm not sure that Venus is losing its atmosphere, but its atmosphere does extend out in a tear shape as it interacts with the solar wind. Probably something that the Japanese will be trying to look at. It's interesting.
Yeah, I'm gonna have to start following that probe to see if they give us any public information on it. It's extremely interesting to me. I mean,
I'm sure they will. The Japanese are good about that, but they, however, some of the information may be lost in translation. But if you've ever seen that Bill Murray movie, you know what I'm talking about. Anyways, let's not get it diverged off too much into Bill Murray yet.
Heard about the new Ghostbusters, right?
Yeah, I heard about that, but I was thinking about a completely different Bill Murray movie.
Caddyshack?
No, it's called Lost in Translation, and it's actually really good, and not a screwball comedy like some of these other things.
I never seen it.
Oh,
that's one of the few Bill Murray movies.
The very young Scarlett Johansson is in it. Yeah, that's enough said. Don't want to get in trouble. But yeah, it's good. And it's a very different character from what you probably expect Bill Murray to play. Yeah, but I love Japan, but yeah, there is a kind of it's difficult to get information across that barrier. Not because anybody wants it to be difficult, it just is.
Yeah, the language barrier is pretty high.
Yeah. Yeah, they've done a fantastic job, the Japanese. They've not only got this mission, they've got new asteroid missions in the works, and they are also doing work on other things. So they've done a good lunar mission. So and the JAXA budget is a small fraction of the NASA budget. You might not think so, but it is actually quite a bit less than the NASA budget in terms of U.S. dollars. In fact, the ESA budget is quite a bit smaller than the NASA budget. And the NASA budget, we all look at it and go, well, $19 billion. Come on, that's hardly grown at all in 30 years, which is true. It really has hardly grown. It really probably isn't shrunk. So $19 billion isn't enough to bomb a small country.
Depends on the bomb you're using.
Well, they have to be very sophisticated bombs.
Yeah.
Aside from various probes in Pluto and Venus, I also hear that the fifth mirror now, or is it more now, has been installed on the James Webb Space Telescope.
Yeah, they did get another one on officially this week. Yeah, got a ways to go yet. They're not going to rush it. They will launch. They will launch when they are ready. That's what the old story is like. Performance, schedule, and cost. Right? Pick any two. Right?
Mm-hmm.
Well, with something like the James Webb, you put performance number one, and then you have to worry about cost, and then schedule just turns out to be whatever it is.
Whatever.
They are on schedule, though.
They are, but that you cannot launch that thing if it's not ready to go.
Not ready.
Yeah.
No,
because they can't go up and fix that thing.
No, they can't fix it.
They can't go back up to like they did with the Hubble, because once it goes up there, it's gone.
Oh, there are people who've proposed robotic servicing. I don't think they've gotten any funding because the Hubble servicing cost a lot of money.
Thank goodness they actually did it, though, huh?
Yeah, well,
I mean, we got the Hubble turned into a mine of a jackpot of usage. It turned out, when it first went up, it was a problem, and after they fixed it and serviced it and upgraded it several times, it turned out to give us a lot of wonderful stuff.
Yeah, well, the James Webb should be wonderful, but as you noted, that it's going to be 1 million miles away, and we're not going to be able to easily. By easily, I mean not without spending billions of dollars will we be able to make any repairs on board.
Right, right. So it's got to go up there. It's got to be perfect when it goes up.
Yeah, it has to be perfect when it goes up, and it has to survive for a long time. Now it should. I think I'm confident it will do well. I think there's a lot of lessons learned from Hubble, but remember Hubble was most of the design work on Hubble went on in the 80s. So 30 years ago. So,
yeah, it's been up there 25 years now.
Yeah, and the technology that was used to put it together is basically 70s and early 80s technology. So it's been upgraded a couple times, but it's still James Webb will be far more sophisticated in terms of, and I think it'll be one of these satellites that outlives its warranty, as many NASA satellites
I think
do.
its primary mission is 5 years, I think.
Yeah, and I'm sure they'll get much more than that.
Yeah, I mean, as long as everything goes well and continues to work well, I guess the first 5 years is scheduled and tabulated and stuff. But don't they continue after that? Just before.
Oh, they'll roll forward with lots of planning.
Okay, now let's do this now. Let's do that now, kind of thing, right?
Yeah, well, it's like the Hubble has been pretty flexible, and this will be a flexible as well. But
I'm kind of wondering if the engineers don't purposely severely underestimate the lifespan and the performance capabilities of some of these.
Oh yeah, we don't call that purposely underestimating. We call that being conservative.
Yeah, I mean, you look at the rovers. Was it Hope or something only supposed to have a 2-year expected lifespan, and like 9 years later it's still going?
Yeah. Well, Opportunity had a 90-day lifespan.
Yeah,
Opportunity. It was 90 days, and unfortunately, they planned their whole science mission around that. So they think we have to go fast, and then after 90 days, they realize this is going to last a lot longer than that.
Yeah. 11 years.
Sometimes you just buy that Walmart clock that usually everybody else buys the same one, and it breaks a couple years later. You happen to pick up the one that lasts 20 years. You ever get one of those?
No, but yeah, I mean, well, the Aerospace Corporation did a study recently where they found that 2/3 of government satellites exceed their lifetime. Their design life. So something like 2/3 exceed their. There's some that don't make their design life at all, but that they're the exception, and then most of them go way past. For example, today I believe the announcement went out that Terra is now the environmental satellite Terra is now 16 years old, and they were joking it's old enough to drive, but it was launched in 1999. I believe it was at that time it was like a 5-year life. I'm not sure, but it's gone way past that. It's still returning a lot. Some of the instruments are not quite 100%, but it is returning science data every day.
Well, what about the solar one, the SOHO? Wasn't that launched in the 70s? Like when I was in high school?
No, not 70s. I'd have to look it up, but it wasn't the 70s.
SOHO?
More like the 90s.
Yeah, it's 10 years old.
Yeah. I might mistake. There's one up there that was launching the.
The ACE. You're probably thinking of the ACE, which has been up there since the 80s. ACE is NL1, and it's still returning data every day. It's 80s or 80s or maybe early 90s. I'd have to look it up. I think as I know some of the people that worked on ACE, and I should know that date, but it's just eluding me right now.
Talking of space telescopes, there's a very impressive piece of work done just this year on the Hubble Frontier Fields program, looking at gravitationally lensed images. There was a supernova that formed what's called an Einstein cross, a gravitationally lensed supernova. And the astronomers predicted that this image of the supernova would reappear this month. And it did.
Ah. Very
impressive.
Yeah.
Yeah. It was a supernova called Refsdal, named after a Norwegian astrophysicist that predicted that you could use lensed supernovas as a probe of the cosmos, basically.
Yeah.
He predicted this in the 1960s.
Score another one for Einstein, huh?
Yeah, definitely. It's a verification of Einstein's theory of general relativity.
Yeah.
It's too bad he wasn't.
It also is. Go on.
He'd be jumping for joy with all this stuff.
Well, Einstein did live to see a fair bit of verification of his theory. So.
Yeah. It's also more evidence for dark matter, because the model of the lensing that the astronomers used to predict when this supernova image would appear was based on dark matter maps. So without the dark matter, it wouldn't have worked. So it's yet more evidence that dark matter is very real, does exist.
Yeah. Now, by the way, 2015 is the 100th anniversary of the publication of general relativity. So probably the single most successful and beautiful physics theory of all time. And it has been verified extremely well up to now. The last big thing is
we need now.
Yeah, we need the gravity waves.
Yes, the gravitational waves.
Yeah.
They're very difficult thing to find.
Oh, yeah.
I think.
Well, the Europeans, ESA just launched a mission as a Pathfinder, a technology demonstrator more than anything else, but for something called LISA, which will detect very long wavelength gravitational waves in space. They're not.
It was good of them to name it after my missus.
Yeah, well, that was. Yeah, that's what it's all about. But now, Lisa. Now there's a ground-based one called actually two interferometers that will look for gravity waves in the United States. One's in Louisiana, one's up in the Pacific Northwest, and they will look for gravity waves. And they'll only count them as a success if both detectors detect the wave at the right time. And they are hoping to get some results over the next 12 months or so. So that should be very exciting. That could be the last check in the box for general relativity. It blows my mind that a classical theory like general relativity could be so accurate, so precise. It's not a quantum theory at all, as you probably know, and describes the big universe dominated by gravity and so exquisitely well. So that's the frontier for physics, is figure out how this incredibly successful, almost perfect theory from Einstein, that's 100 years old now, can somehow find its place in the standard model, which so far has been a completely unsuccessful attempt. So it's String theory says they
I
can
think
do it.
it'll happen.
Yeah, I think it probably will, but it's going to be a multi-generational enterprise. It's going to take a long time. All the low-hanging fruit, is gone, apparently. You won't get another Einstein. You won't get somebody who can sit down for a few years and think through a problem and revolutionize physics. Just can't.
Probably not.
It'll take teams of hundreds of very clever people working for generations to come up with that.
Yeah. Well, quantum physics is such a strange area of physics. It's just difficult. It's hard. Quantum gravity is not an easy problem, is it?
No, and the problem is
so incredible.
It's really difficult to get empirical data about quantum gravity because these things happen at you don't expect to see anything at just energies that really they only can be obtained shortly after the Big Bang. We can't build a particle accelerator that can get there. So that's
there's been some interesting new results just recently from the Large Hadron Collider at CERN in Switzerland.
Yeah, I saw that this week.
They may have found a new particle. I say may, it's very tentative. They found a bump in the data which may suggest a new particle, quite a heavy particle. I think something like 750 giga-electron volts, which is a big particle.
That's a big particle, yeah.
Which could be a dark matter particle. But these bumps in the data sometimes go away. It's too early to say.
Yeah, just to give you a sense of that, the proton is less than 1 giga-electron volt. It's like 900 something mega electron volts. So this is something hundreds of times heavier than the proton.
What was the Higgs boson? Was it something like 125?
That's what I recall.
Around there. So yeah, 750 is ridiculously large for a particle we haven't yet ever seen.
Yeah, it's very well. That's why you build big colliders like that, is to find those strange things.
Yeah.
When was this? When did they run this one?
Well, they've been running it for the last several months, but they announced it this week.
Yeah.
They announced it this week?
Yeah. It takes many runs to get any statistics on these guns.
Yeah, sure.
It's based on the new higher energy runs that they've been doing just over the past few months. The energy level's been boosted, hasn't it, this year?
Yeah. There was something like almost twice as much. I forgot the numbers. The Terra electron volts, I forgot the numbers.
Yeah. It's not important, really. But things aren't looking good for supersymmetry. One of the things they've been looking for is evidence of supersymmetry. And they've found none. So for those particle physicists and theorists that have spent their entire careers working on supersymmetry, I would imagine they're not happy, not at all happy.
Right. Well, or, maybe they are. I don't know. But I mean, by the way.
I know that there was one guy that was really trying to push for it and insisting that it's still real and kind of hard-nosed about it. But I think the majority of the physicists were saying that they were disagreeing with it, and there was one or two holdouts that were saying, no, it's real, it's got to be.
Supersymmetry is a very elegant theory that would solve some of the holes in the standard model. It would explain the mass of the Higgs boson, and supersymmetry basically is an extension of the standard model that says every particle has a partner particle, and these partners have masses that cancel out the masses of the the other particles, and it all makes it fit together very neatly. And if they find that this isn't the case, it means that they've got to go back to the drawing board, and the standard model still has holes in it, basically.
Yeah, well, there's a lot of unanswered questions, although the standard model does describe an awful lot of what we see there very, very accurately. So it's the question. People would love to find physics beyond that and answer the question of what is dark matter? You know, we know it's there, but what is it?
Yeah. Well, supersymmetry provides a dark matter candidate particle. Yeah, the lightest supersymmetric particle in supersymmetry would be a stable, electrically neutral particle that is weakly interacting, and that could well be a dark matter particle. But yeah, it doesn't matter how elegant, how well a theory fits together. If it doesn't match observation and experimental results, it's got to be wrong.
Yeah.
So,
but you know, that's what we have to face, is that where we are in physics now, you're going to have whole generations that go down blind alleys. And
yeah, sure.
Because all the low-hanging fruit is gone. I say that perhaps too glibly. Maybe there's something out, some incredible new insight waiting to be discovered.
I don't think it's too late for supersymmetry.
Yeah.
Maybe the energies that the Large Hadron Collider is operating at is still not high enough to see supersymmetry. I don't know. I'm not a particle physicist, but if they don't see evidence of it by next year, I would imagine it's going to get thrown out. We'll wait and see.
Well, yeah, but there's an awful lot of stuff that we're not going to run out of problems to solve for a long time. And much of normal science is problem solving, that is, or what Kuhn called puzzle solving, that is, try to figure out how it fits into the paradigm you have, and then every once in a while you say, this isn't going to fit, we have to start over with something new. And I think we may be getting close to that point now, mainly because of success of the standard model, which is very, very good at predicting what goes on at the Large Hadron Collider. And so if you recall the 19th century, I do clearly, people were saying things like, well, we pretty much understand everything about physics now. We just have to figure out this Michelson-Morley thing and the black body spectrum, and we'll be done. And of course, they figured those out, and physics was completely turned on its head.
Right. I think we're probably at one of those stumbling blocks again, like kind of like a writer's block, and it happens every so many decades. You come up, like you said, you come up to the point where you say, well, I think we figured everything else out. What else is there left? And then all of a sudden something comes along and said, oh, wow, what the hell is that? And all of a sudden a whole new set of experiments and things have to be made to figure this out. I think we're at one of those thresholds at the moment. I think it's this dark matter thing, for example, is one of those thresholds where we seem to be at a point of sort of stalemate until it happens.
It's entirely possible that sometime in the next few years, dark matter will be resolved. I don't want to rule that out. It maybe just be a standard puzzle solving exercise. Then we'll know what it is. And we're not there yet. And until we are there, nobody knows whether it's going to be a revolutionary change in physics, or it's just going to be something that fits into the model pretty well.
Well, what I mean, in other words, the stumbling block is in other words, it happens every few decades, and it seems like we're at that point. Now I use dark matter as an example, but it could be almost anything. I think something is going to come up, like you said, within the next few years. Somebody or something is going to come up and say, "Hello, by the way, did you know about me?" You know, or somebody's going to come up and say, "What the hell is that?" You know, and they're going to realize, and it's going to start up again. It's going to all of a sudden technology is going to flood again, and then another 10 years or so is going to slow down again. You know, maybe we'll get into deep space travel by that time.
Well, you know, it's like Freeman Dyson said, there's the mountains and there's the jungle, right? Physics, high energy physics is the mountain, you know, the very fundamental sort of thing. But down in the jungle, like what happens on a Kuiper belt object, you know, when it evolves, there's also lots of interesting stuff going on. Doesn't require any new physics, but it does require a new understanding, and that's you know, that analogy says, you know, we might be learning, we might spend some time exploring the mountains, but then when we go down to the jungle, we find all kinds of interesting things going on there too. So, and the two things may not be completely uncoupled. There may be things we'll learn in the jungle that can help us understand the mountain. So, that I'm pretty optimistic that even if physics is done, that is, there's no more physics that we need to understand anything we can do with a real particle accelerator, then there's still a lot to learn. And
I don't think it's ever going to be done. I think there's just going to be stumbling blocks.
Well, you know, we'll find out. And it may be our grandchildren or our great-grandchildren who look at the data one day and say, "Oh, that's funny," and then we're on to the next chase.
I mean, look at the biggest, of course, thing is the propulsion systems for space travel. For the longest time, the fastest thing we had was a rocket. So what's the top speed of our top rocket is 20-something thousand miles an hour, and that's as fast as we can go without any gravity assist. Then somebody finally come up with the ion engine. While it's not a very powerful,
the ion engine is a rocket. I mean, it's a moment.
It's the amount of acceleration is very, you know, gradual, but nevertheless, we're talking now speeds of 60,000 miles an hour or better.
The speeds aren't really what you get from a rocket, right? You get momentum exchange.
Right, that's what I mean. In other words, we have to figure out ways of faster propulsion, and so far we slowly but surely we're getting there. And the ion engine is one example. The next step, I think, would be a more efficient ion engine or a more powerful ion engine.
Like I said, an ion engine is a rocket. It's just a very weak rocket.
Right.
It's a weak, highly fuel efficient rocket. It's like the difference between an old V8 Cadillac and a smart car.
Right. I'm comparing liquid fuel to ionic. You know.
Well, it's just xenon.
Okay.
It's fuel. It's still fuel.
There's still fuel, but I'm trying to give the analogy of the different. You know, in other words, the fastest solid rocket booster rocket, you know, that we're used to, the Saturn V, you know, the fastest thing that we have with all that flame coming out of the back is something of the neighborhood of 20,000 miles an hour, whereas the ion engine.
Well, no, you can't get stuck on speed.
Well, what I'm trying to say is we have to get faster if we want to go further.
Right, but it has more to do with mass fractions. That is.
What I'm trying to get at is the technology in order to get us up to that speed. And so far, we did manage to get the ion engine, which I think is something in the neighborhood of a possible 60,000 miles an hour. And
no. It's not the speed again. it has to do with how much momentum you can transfer to a payload, and speed is not inherent in that.
Well, I mean, isn't it, you know, the fastest you can go is as fast as the stuff is spitting out the back. I mean, you know.
No, that's not true.
That's not true?
No.
That's what I was always been told.
It's Newton's third law. If you get a reaction out the back and how fast you can go depends on how much fuel you have to burn. Yeah, I mean, there's something called ejection velocity, which is also called specific impulse. I'll put some references to that in the show notes, but that's how fuel efficient a rocket engine. It's not how fast you. So now to build engines that are going to take large payloads to, all around the solar system, we're going to need both highly efficient and high power engines. And that's something that we don't have. We have inefficient rockets, and we have very, very low power ion engines or Hall thrusters. Hall thrusters are basically ion.
Well, let me ask you a question then, since I have to now create a hangout sometime in the next few days and tell everybody that I was wrong about what I said in the hangout. Let me ask you a question. I'm going to give you a simple analogy, and don't tear me apart because I'm being simplistic, but say I got a satellite or a spacecraft up to let's call it 100,000 miles an hour. Are you telling me that I can, if it was equipped with some kind of even small rockets, that I would still be able to accelerate that while it was moving at that speed? I would still be able to accelerate that with a simple rocket?
Yeah. Yes.
See, I was under the wrong impression that
the problem you get into 100,000 miles an hour is not that fast, but
well, I was giving an example. I mean, because I was under the impression that let's call it 500,000 miles an hour then. But I was under the impression that the exit speed of the stuff coming out of the back, the accelerator, was the limitation on the top speed of the vehicle.
No. In fact, that relative to yourself sitting on the rocket, it's still the same speed. So
no matter how fast you're moving, you're still going to move it faster.
Yeah, the problem is you get into something called the tyranny of the rocket equation, where you have to carry fuel, push the fuel that's pushing you, right? And so it's an exponential buildup of the amount of fuel you need. And if you start going really fast, the amount of fuel just goes insane. And so, you can only do so much with a rocket, and if you have a more efficient rocket with a higher ejection velocity, like an ion engine, that buildup is slower, but it's still inevitable. And also, right now, ion engines, I think that the best ion engine I've seen on the books is a few kilowatts. That's not going to feed the bulldog. You need megawatts, tens of megawatts or more. So right. We're not there yet. If you really want to zip around the solar system, you're going to need hundreds of megawatts.
Right. That's what I was getting to earlier when I was saying that the next breakthrough in science is going to be higher efficiency propulsion. Well,
I think that's really, we can get the higher efficiency if we can get the high power. Now, how do you get high power in space? Well, nuclear, right? Either nuclear fusion or nuclear fission. Fusion would be my preferred. Helium-3 is my preferred solution. I think it's clean and doesn't cause a lot of trouble. And you can also get helium-3 on the surface of the moon or on surface of asteroids. It comes out of the solar wind, basically. So,
there's been some experiments done recently in Germany with a nuclear fusion engine.
Yes,
it's been successfully tested, very briefly tested, but that looks good. Looks good for the future.
Yeah, the Stellerator. Now, this is a big, heavy thing. it's still magnetic confinement fusion, which may be the only way to do it. I don't know, but that's practical. But I'm not sure exactly if they've. I know they've turned it on and they've done some shots. I don't know if they're broken even or not.
I think that they only turned it on for like 0.1 seconds. You know, they're only at the initial test stage, so it's too early to even say whether they got more energy out than they put in. Yeah. I don't even think they're up to that stage yet. They're still testing, but they're heading in the right direction.
Yeah. I think for a space fusion reactor, we're going to need to see, it's going to have to be helium-3. And the reason for that is helium-3 doesn't produce neutrons, which are damaging to the equipment around them. So unless you can figure out what to do with the neutrons, you need helium-3. Now, you can make helium-3 on Earth. You can, it's just a decay product of tritium.
Mine it from the moon.
You can mine it from the moon, or you can make it with a fission reactor, because it just, when tritium decays, it turns into helium-3. And well, some of the decay products are helium-3, and you can use it there. But yeah, you can mine it from the moon, or you can mine it from the asteroids. And how much you can get, I'm not sure, but you don't need a whole hell of a lot. You just need a little bit to get. But the problem is nobody's built a reactor that uses helium-3. Even, and certainly nobody's broken even. So, and right now, they don't need it for terrestrial applications. So, I'm not sure what's going to happen there. You could use fission. And as you know, there's been some opposition to bring nuclear power into space. But in the 60s, the U.S. tested a nuclear rocket. It never actually flew, but it was tested on a static flight test, and worked. It worked.
Fission seems far too dirty to me.
Well,
you have nuclear waste.
You do have waste, but in space, would you care about waste? I don't know if you would.
Yes, definitely. We can't if we start off just polluting the solar system, that's just not going to go away. It's going to stay in the solar system. We can't start sending out nuclear fission engines and just ditching nuclear waste.
Well,
I completely agree. I mean, you can imagine if it starts to take off. These great new engines that do all these wonderful things starts to take off, and in the meantime we're irradiating our solar system, poisoning everything around us, and sooner or later, when we want to go ahead and perhaps colonize any particular body or something like that, we find that
well, there's an awful lot of bodies that nothing's living on. We could
just because we're happy to pollute our own planet doesn't mean we should extend the same policy to the rest of the solar system.
But what's wrong with putting nuclear waste on an asteroid, for example? It's not going to harm anything.
I could see disposal, ideas for using asteroids and stuff like that. But when we're starting to talk about possibly exploring further beyond, and even in our own solar system, for example, the moons and stuff, we have to be careful. We've talked about this in some hangouts about contamination of particular bodies, even just with biomaterial. But also, I think nuclear waste and radioactivity and stuff is also a consideration.
Yeah.
I'll take your point. We bury it on an asteroid, bury it somewhere out the way.
Well, you don't have to bury it. You just have to park it there, right? As long as there's enough gravity to hold it.
Not even that, really. There are some nuclear reactors that can use waste from other reactors.
That's true.
They'll run on that waste. They're still in the design phase because were really slow at adopting nuclear policies, but once they get, once the permissions get through and they're started being constructed, they could probably scale them down for various types of interstellar craft.
Yeah, well, I don't know about interstellar, but certainly interplanetary. I think we're gonna have to learn to. We're gonna have to walk before we can. We're gonna have to crawl before we can walk.
Yeah, I mean interstellar.
We're crawling now. We can.
Yeah.
Walking would be able to travel around the solar system straightforwardly.
Also, if we're able to send something to an asteroid, and we're talking about nuclear waste, and it's not a whole lot of stuff when it comes to the size of the sun. If we could send something in one direction, we could certainly send it right to the heart of the sun, and just say goodbye to it and let the sun take it. The sun incinerated for us.
Set the controls for the heart of the sun. Is that what you're saying?
Yeah.
Well,
Pink Floyd fan.
More nostalgia than anything else, but no, there's problems with that. Then you've got a big delta V to get into the sun. Not easy. But yeah, it would do no harm in the sun. It would do no harm most places. There's only a small number of habitats in the whole solar system that we really have to worry about contaminating. So that, and I don't. There's no reason why we have to worry about contaminating them if we do it right. There's already planetary protection issues with Mars, but that's probably probably a subject for another episode. Speaking of which, we're coming down to the end of this one, and maybe it'd be a good time to go to our quick recommendations. Hopefully you've all been thinking about those all week and agonizing over them and losing sleep over wondering if they're right but even if you haven't, it's still time. So let's start with you, Adam.
I was going to recommend that people look at the images that Cassini is going to be taking in about 8 or 9 hours' time of Enceladus. It's on its very last flyby of Enceladus. And it's going to be imaging the South Polar water geysers. I did write down the web page, but I'm struggling to find it. It's something like NASA.jpl. No, it'll be Cassini.jpl.nasa.gov. I'll sort the proper.
Yeah, I think that's right.
Yeah.
And
it takes about three or 4 days after the event for the images to get back to Earth, but then NASA put them up on the Raw Images website. Right. There should be some stunning pictures of Enceladus appearing on that web page in around 3 or 4 days' time.
Okay, so sometime
other than that,
yeah,
I would recommend that people go out and look at the full moon on Christmas Day.
Ah,
we've got a full moon on Christmas Day.
I hope that
won't happen again for 30 years or something. So have a good Christmas and look at the moon.
Okay, how about you, James?
Okay, I've got one. I figured I'd gear one towards you, Paul.
Oh.
There's an anime out there that I've loved for years called Cowboy Bebop.
Cowboy Bebop.
Yeah, it's about a couple of bounty hunters. It's about a couple of bounty hunters in space. They pick up a child genius and a gene-modified dog named Einstein. Excellent animation, really great story, and some really damn good jazz music throughout almost the entire series.
Huh.
I figured you'd go for the music at least.
Yeah, that I would.
Yeah, it's got one of the best soundtracks, I think, of any anime out there.
Okay, so I've got from Adam, I've got the Enceladus images, plus looking at the moon on Christmas. James, Cowboy Bebop.
Yeah, I'll send you a link to the Funimation homepage for them.
And okay, Patrick, you got to top those too.
Well, to tell you the truth, Adam took my full moon on Christmas thing. James took my Cowboy Bebop, and incidentally, I wish I could remember his name off the top of my head, but believe it or not, that wonderful jazz music, it comes from a Japanese guy. And I'm trying to remember his name, but I would recommend you look that up. So since they were
some of it comes from American artists too.
Okay. Anyway, since those were taken, I'm going to recommend instead an idea that is, it shows that this episode shows that scientifically minded and scientists. I'm just a scientifically minded. I'm not a scientist. I'm a science enthusiast. Can be wrong, and I actually learned something tonight. So I'm going to have to create a hangout and apologize to a couple of people I was hanging out with to tell them that I was wrong about that and they were right. So I recommend to learn more about what a scientist or what science is really all about, and how scientists can say, "Oh, I was wrong." So there you have it. Patrick Festa says, "Oh, I was wrong," and Paul Carr was the educator for that reason. It had to do with the rocket speeds and things of that nature. So that's what I recommend.
Okay. I'm typing as I go here. Okay, my recommendation is a website. I think I'm doing a website that is, yeah. And it's been a favorite website of mine for many years. It's called spaceweather.com. That should be easy to remember. It's a terrific little page. You can pretty much get everything you need to know in that one page. And it not only does it summarize for you what's going on in space weather, there's beautiful images of things like noctilucent clouds and auroras. And he has very good taste in picking good photographs to look at. There's a picture of the current sun with all the whatever sunspots are out there. There's information on the solar wind and asteroids that are passing near the Earth and when they'll pass by. All kinds of fun stuff like that. So, again, spaceweather.com, a really well curated site. And I recommend you go looking at it and maybe click on the ads a little bit. Provide some support. Okay. So that is it for episode 37. I'm happy to say I made it through this one without collapsing. Thank you, guys. This is episode 37. It's the 18th of December, 2015. We will be back next week. Not next week, sorry. At the end of the first week in January. January 8th. And so we're taking not only Christmas off, we're taking New Year's off. And we'll be back January 8th, or probably see it on your RSS feed January 9th. And then every Friday thereafter in January. Now, couple of things. This is an open participation podcast. If you want to be on the panel, just like these guys, you can do so. Give me an email at unseenpodcast@gmail.com, and I'll get you set up to be on the panel. Essentially, what you have to do is join our Google Plus participants community. Now, if you have been in the participants community, that is for people who are engaging with the podcast, participating in the podcast. There's also one for people who just want to listen. There's also a subreddit for people who want to listen. And the links to that are at unseenpodcast.com. So please go to unseenpodcast.com. You can learn everything you need to know about this podcast, including how to participate and who has participated before. We have 20 unique panelists on 37 episodes. And we are hoping in 2016 to have another 20 new panelists. So maybe more. And I don't know why it wouldn't be you. So please join us. And again, that's unseenpodcast.com. And also, we are a spinoff of the Wow Signal podcast. That's wowsignalpodcast.com. That's a more structured, more edited podcast than this one. So do feel free to go there and have a look at what we've done recently. Most recently, we featured a couple of discussions of SETI-related issues by Nick Nielsen, who's a frequent panelist on this podcast as well. So, we hope to see you in early January, and we hope you'll subscribe to the podcast. If you want to support the podcast, go to patreon.com/unseenpodcast and sign up for a small amount of support per month. We recommend $1 a month. We think that's affordable to almost anyone, and will, if just a small percentage of our listeners do that, it will cover all of our costs. So be that small percentage. Okay. So I'd like to thank our panel tonight. It has been Adam Smith.
Happy holidays. May the force be with you.
I point out Adam's in the UK, so it's very early on Saturday morning there. And James Garrison.
As always, it's been a pleasure, Paul.
And Patrick Festa.
Thank you again for having me on a short notice. Happy holidays, whatever it is that you celebrate, and hopefully I'll see you in January.
Yes, happy winter solstice to everyone, and we'll see you in January. This has been episode 37 of the Unseen Podcast. For more information, go to unseenpodcast.com. Music by DJ Spooky. Good night.